I'd like to give you a bit of an introduction to applications of reaction orders. So what we've got here is an example of two reactions, an SN1 and an SN2 reaction. Don't worry too much about what these mean, but the nucleophilic substitution reactions, that's what the N and the S stand for. And that's your SN2 and here's your SN1 over here. Now it turns out that we can do some experiments, and the kinds of experiments we do are the kinds of experiments we did earlier, and that was to vary the different concentrations and figure out initial rates, and that would allow us to get some reaction orders. And experiments were done on this particular set of reactants where we've got the C4H9Br, that's this one here, and the Cn-, and it turned out, it was found by experiment, that the rate equation was rate equals K, C4H9Br, and Cn-. So both of those are involved, they're both to the power of 1. And what that tells us is that both of these are involved in some sort of reaction. And the kind of reaction they came up with involved both the Cn- and the C4H9Br, and that's what they popped out with. So they got that all from the rate equation and knew that since these were both controlling the rate, that they were probably both involved in some reaction together. Now that's contrasted against the SN1 reaction, which has a slightly different reactant. You notice this is a straight chain here, and this one here is a branch chain, and the Br is sort of in the middle there. Now it turns out when they did the same kind of experiments on that one as they did on the previous one, the rate equation came out to be rate equals K C4H9Br. Notice there's no Cn- anywhere in here. So the rate does not depend on the C4H9, so the rate does not depend on the Cn- at all, it only depends on the C4H9Br, this one here, and that's it. So the kind of thing they came up with as an explanation for this was this kind of thing, where they've got the C4H9Br having the Br leaving in some sort of slow step, and then the Cn- attacking in some kind of faster step down the line. Now the whole point of this is that the rate is only going to, the rate equation is only going to tell you what's going on in the slow step, because the rate depends upon what's happening in the slow step. Let me give you some sort of explanation for that. Alright, so let's say you've got a freeway, and it's like a 4-lane freeway, and then suddenly there's an accident and you only got one lane, and then after that it widens out again into, say, a large number of lanes, and you're trying to go from here, which is A, to B. So you're going to start out here, you're going to be going merrily along, and there's no problems there, but then you're going to get to this bottleneck, and there's going to be a whole lot of other traffic trying to get through this bottleneck as well. So what's going to happen is how quickly you get from A to B will be determined by what's going on in this bottleneck. And that's what we're going to find with rate of reactions as well. Rate of reactions depends on slow step. Just as though your journey from A to B is also going to be determined by how quickly you can get through this bottleneck here, through this slow step. Alright, so going back to our example, you can see that what's going to happen here is, because the rate is only dependent on the C4H9Br, we know that that's going to be what the slow step is. So the rate equation will tell us what's going on in the slow step. And I'll say that again, this is really important. The rate equation tells us what's involved or what's going on in the slow step. So the slow step only involves C4H9Br. So that's how they know that the C4H9Br is the only thing that's reacting in the slow step. And then the Cn- comes in some kind of faster step at the end. Now the other thing that's important is that we also know that this is more than one step, because the Cn- is not involved in the rate equation. Since there's no Cn- here in the rate equation, and we know that it's involved in the overall reaction, then what we've got to assume is that there's going to be something that involves C4H9Br, and then later on the Cn- is going to have to be involved. But going back to the previous one here, we knew that this was going to be a single step because everything that was in the reaction was going to also be in the rate equation. Now over here, no Cn minus, so we know the Cn minus had to be involved in some kind of second step. So not only does the rate equation tell us what's going on in the slow step, it can also give us a clue as to how many steps might be involved in the actual reaction process. And that's what we're going to be analysing in a different set of problems.